In this video, we'll take a look at the derivative of different forms of the exponential e. So we have the log base e, which gives us natural log, and exponential growth, e to the x, and exponential decay, e to the negative x. And all of this is based off of e, where you probably are familiar with, right? So somewhere around 2.7. And this is also known as the natural number or Euler's number. And it has a lot to do with growth and decay. And we'll briefly talk about where e comes from, and we'll see the unique properties of the derivative of natural log and e to the x, or e to the negative x, that makes solving a lot of these physical systems that have this growth or decay or asymptotic properties much more convenient. So here we have the graphs of natural log of x, exponential growth e to x in blue, and exponential decay e to the negative x in green. Both growth and decay have a lot of physical significance, and they show up a lot, and so they're great to e to x and e to negative x are great to understand, and the derivative of those forms show us the rate forms of those, and those also show up a lot. So the convenience of the properties of the derivatives of e to the x and e to the negative x is a big reason why they are used a lot. So you'll see growth and decay, and you can see that you have a horizontal asymptote here and a vertical asymptote here, and a horizontal asymptote here. And you can shift them, right? You can imagine how you add terms to either of these to shift where these vertical or horizontal asymptotes show up to fit your physical system, whether it be like a battery charging or discharging, whether it be some kind of material heating or cooling over time, right? So you can see all those show up. So we'll briefly talk about where the origins are, build some properties defining E, and then we'll do some derivations. So the natural log of x is basically log base E. So all the properties of logs are true for a natural log, right? So natural log e to x, the same thing as saying like log base 10 of 10 to the x is just going to be x. Similar, e to the natural log x is just going to give you x. So that's convenient, right? So just understanding those rules will help us apply the derivative terms. All right, so your e value, where does it come from? So there are a number of great YouTube videos that talk about compound interest and where this e value comes from a continuous compound interest. So the concept I'll briefly explain it here, is saying like if you looking at compound interest over a period of time and then splitting up the interest into that period of time, you can look at this as 1 plus 1 over that interest over that period, the incremental piece of time, period of time, to the power of n, where that is how many interest terms you have, right? And E is basically saying if I take those increments of time and taking it to infinity. So you have one period of time and you cut it up infinite amount of times and you break up the interest across that time. That's like thinking about this as continuous compound interest. And that's a definition of E. Now, we'll find that it's convenient to also write it in this form where I'm just using a substitution. So I'll briefly show where this comes from, right? So if we define a dummy variable a as 1 over n, then I know I can change my limit from an n approaching infinity to a limit of a approaching 0, right? That would be the equivalent there. So if I use this as my foundation equation, I can derive this form of it. And a and n are dummy variables that we can substitute when we do our derivative terms. So limit of a approaching 0, and I'll use this equation as 1 plus 1 over n, we substitute with a, and substitute n with 1 over a. And I'll apply the limit on both sides of this so I can get my 1 value at the end. All right, so limit of e as a approaches 0. Doesn't change anything there. All right, now we just use simple algebra to manipulate this. So I can say limit of a approaching 0 of 1 plus a. I'll take everything to the power of a. So I get limit of a approaching 0 e to the power of a. Limit of a approaching 0 of a is equal to limit a approaching 0 e to the a minus 1. So subtract 1 from both sides, and then I can divide by a on both sides. I'll get 1 here, and I'll get e to the a minus 1 over a. Limit of that as a approaches 0 equals 1. All right, so that's how I get this form here. Now we'll use both of these forms in different derivations of my exponential decay or growth. And so we'll look at the derivatives of these by taking the limit of the rise over run terms like we did in the previous video. Just a fundamental definition of derivatives. So we're going to take the derivative of natural log of x. We're going to use our limit equation, taking the limit of the step size as approaching 0, and this is just basically rise over run, right? So if we plug in our equation, we get natural log x plus delta x for my yx plus delta x term, that's showing up right there, minus natural log of x for my yx term, that's showing up right there. And then I can combine my numerator into a single equation because of a rule of logs. This can be rewritten as natural log of x plus delta x over x. Okay. Then this is all divided by delta x, which is essentially the same as multiplying by 1 over delta x. So again, another rule of logs, I can take that to the power, right? So this divided by delta x can be looked at as 1 over delta x, and that can be the power within the natural log. And then we could simplify what's inside this natural log as x over x is just 1, and then delta x over x, right? That's how we get this form here. And essentially what we're going to try to do is take this form and grab a natural log e term from it. Okay, so we're going to try to make it look like this property here. So we're going to do a substitution to help us with that. And you'll see that we'll do more and more substitutions in derivatives principles as well. Here we're doing it for a limit, but it's also very useful for derivatives. And we'll see that in future videos. So we make the substitution that n is equal to x over delta x. And essentially we know what we're trying to make it look like, and that's part of the reason, right? So we see a delta x over x term here. And so if we make this look like 1 over n, that's going to help us reach our get closer to our goal. So we say that this equation is equal to limit of n approaching infinity. So why is n approaching infinity? So this is delta x approaching 0. So delta x approaching 0 will make this term go to infinity. So n approaching infinity is equivalent there, right? Then we got 1 plus 1 over n for this substitution here. And then we got 1 over delta x. 1 over delta x is going to be n over x. So n over x. But I want this to look essentially like this equation here. So I don't want this x term to show up in this exponential. But I could just pull that out here because of the rule of logs. So I have 1 over x times this form, or essentially this form right there. So the limit of this is going to be e. 1 over x has no influence on the n approaching infinity term, so we can pull that out. Then we get 1 over x natural log of e. Natural log of e, if we remember before, is just going to be 1. So I get 1 over x. So the derivative of natural log is just going to be 1 over x. We'll do the same thing for each of the x, and this time we're going to use this form of the natural number definition, but we'll see what that looks like. All right, so again, we use the rise over run limit for the derivative definition and plug in each of the x. So I get e to the x plus delta x, that's my yx plus delta x term, and then e to the x, that's my yx term. All right, so this is the equation we get. And then we can do some exponential, apply some exponential rules. So e to the x plus delta x is the same as each of the x multiplied by each of delta x. Then I can factor out a common each of the x in both of these two terms, right? Both of these two terms. So each of the x times each of the delta x minus 1. That's what we have here, right? So it's getting close to look like this form here. So I can pull out this each of the x term, and then we have limit delta x approaching 0, each of delta x minus 1 over delta x. That essentially is this, where a is delta x. So this is equal to 1 to get each of the x times 1. Each of x is equal to the derivative. So this is part of that convenient form. It itself, it is the same as the derivative of itself. And so that makes solving a lot of these rate terms involving each of the exponential growth very convenient. So the next step is to see, right, what is the exponential decay going to look like? Is it going to look similar to this or have similar properties? So we'll see that in a second. All right, so we're going to basically do the same thing we did for the exponential growth, but now we have this additional negative sign in the exponential for exponential decay. So we plug in our functions, we get e to the negative of quantity x plus delta x, that's what we have here, minus e to the negative x. Again, we do the same thing, we split this into two terms. We get e to the negative x times e to the negative delta x, right? Just factoring the negative, distributing the negative sign into both of these terms when we break it up into multiplication of these two decay terms. All right, then we can factor out e to the negative x. So then we get e to the negative x times the quantity e to the negative delta x minus 1 from this term here, divided by delta x, and taking that limit. Again, we're trying to get this form to show up in some way. So I can factor out by e to the negative x because it has nothing to do with the limit term here. Then I get limit delta x approaching 0, e to the negative delta x minus 1 over delta x. Now we're really close, but here I have this extra negative sign. So how do I get rid of that? I can do a substitution. So I'm going to substitute n as negative delta x. And so we're going to do a substitution here and here. So e to the negative x, that doesn't change. Limit as n approaches 0, as delta x approaches 0, n approaches 0, right? Just by the substitution relationship. So that stays going to 0. Then I get e to the n, right? Negative delta x is n. That's what we are substituting here. Minus 1 divided by delta x. Delta x is negative n. So I have a negative n here. So I'll pull this negative term out and attach it to this e to the negative x term. That's what we show up there. Then I have limit n approaching 0, e to the n minus 1 divided by n. And now we look just like this. And so that's equals to 1. So negative e to the negative x is equal to the derivative of your decay term, e to the negative, derivative of e to the negative x dx, right? So now that we have these, let's take a look at the graphs and understand, at least graphically, why these are the derivatives, at least from a sign perspective, that they behave the way that we would expect. All right, so we can look first at the natural log. So here in the solid red, we have the natural log function. We see that we have a very large slope initially, and then it gets smaller and smaller and smaller and smaller as x grows. So we can see if 1 over x, the derivative, mimics that, right? It's the function 1 over x starts off very large, then it gets smaller and smaller until it gets closer and closer to 0. So it does reflect the derivative of ln x. Each of x, both graphs here are just stacked on top of each other. That's why you only see one line here. But let's see if it is reflective, at least in the same way, right? So it starts off with a near 0 slope. Then the slope starts increasing until it gets very, very large. The entire time, the slope is never negative. And then if you look at the graph again and compare it, right, it's basically 0, a y value of 0 out here. It's never below 0, right? So that's consistent with the derivative form that you would expect. Then it starts increasing, and then it increases very large as x increases. So it's consistent there. Then we can look at the exponential decay, right? Each of negative x is shown in this solid green line. It starts off a very large negative slope that's reflected by negative each of negative x, right? A very large negative y value. Then the slopes gets closer and closer to 0 until it's pretty much 0 as your x value increases. And so if you follow the y value of the negative each of negative x, it gets closer and closer to 0 as x increases. So at least from a sine and growth perspective, they are consistent here. Now we can use these different tools and combine them, and we'll look at different derivative rules that will allow us to look at larger systems of more complex functions and take the derivative of them.